Hello, everyone. So last week we looked at the theorems of exponential functions and logarithmic functions. We kind of look at one or two applications, but today we are going to explore more on the on the applications of exponential growth or decay. I would want to mention that exponential functions are vast and span across numerous fields, including the sciences, economics, and engineering. Tonight, I want us to look at some specific, applications, and some areas include, population growth, compound interest, radioactive decay, Newton's law of cooling. And then, if time permits, we'll also look at in the area of epidemiology, which has to do with the study of how diseases spread as they emerge in a community. Stay with me, so even as we kind of explore the journey together. All right. So suppose that P is a population size, then the differential equation there is equal to P. We kind of claim that it represents the sample model of exponential function or exponential growth or probably decay, depending on the sign under the sign of the constant K. All right. So in that case, we can kind of say that the K, represent the rates, the rate and nature of the growth or decay. Okay. So I want us to take note that P in this case, we said it is a population size. And then the K, we kind of want to say that or point out that it's a constant that determines whether the population is growing or decaying. So I want us to take note because I'll be making reference to that. So let's kind of understand the fundamentals, okay? Good, very important. All right. Now, how do we interpret this? How do we interpret this? So since P, we know that is a population, we can interpret this as at the rate of change of the population, okay, as it is proportional to its current population, okay? Very good. So I want us to take note that the rate of change of the population is proportional to its current population, okay? So let's take note. Very, very important. All right. Now, I would want us to maybe point out one or two things over here. And so for the interest of time, I would want us to, just focus on just the exponential decay. Okay, for the interest of time, I want us to do that. All right. Now the question is, how do we find solution to such a differential equation? Okay, so we call this one a differential equation. How do you find a solution to such a differential equation? How do you find a solution to such or the general solution to such a differential equation? Okay, so the solution of this will just be the population at time t will be equal to the initial population. So let's name it as P naught, okay? P naught. Then since we are talking of exponential, okay, so we are going to have e to the power k multiplying t. At this point, I will not kind of go through how we obtain this, but this is the general solution of kind of getting our P. Is that okay? How about let's see how best probably we can get this, okay? So how do you find the general solution to this? I think let me do that instead of just going straight to the point. So for us to kind of solve such a problem, what we can do is to use the method of separation or separation of variables. Okay, so we can just use a separation of variables to kind of solve this problem. All right, so in that case, if you use the method of separation, so what we can do, we're going to have d on p equal to k dt, right? Okay, so if you're going to do that, then we can, at this point, what we can do is to apply the integral on both sides. Okay, so by applying integral on both sides, we are going to have so we are going to have the, because if not done the integration side, that's why I don't want us to go straight into this. So I want us to pause over here, okay? So I want us to pause over here because we've not done the integration. So I want us to pause over here, then we'll exploit further, okay? All right. Now, the general solution of this differential equation is P of t equal to P naught e to the power kt, okay? Very, very, very important. And so over here, we claim that if k is less than 0, then we have exponential, okay? So if k is less than 0, then we'll have exponential decay. Okay? And then if k is greater than 0, then we'll have what we call exponential growth, okay? So I want us to, take note of this. These are very, very important. So I want us to kind of take note. All right. So at this point, what I would want us to do is to look at areas where we can kind of apply such concept. Okay. So let's look at some few examples over here. So before we kind of look at the applications, I would want us to know the nature of the graph of exponential growth and exponential decay. Okay, so please let's take note as we look at it together. So if I have such a graph, if I have such a graph, let me say on the horizontal axis, that's my time, and on my vertical axis, that becomes my response variable. Let's call it y. Then our exponential growth would behave this way. Okay, let me this, I don't like this graph, so let's use a different one. So our exponential decay will be as this. So this is a time where it starts. Okay, so this was what we called our P naught. That is our initial value. Okay, this is what we called our P naught, our initial value, and we claim that this is the growth. This is where there's growth. Okay, this is the stage where the population is growing. This is the growth, and we also said that this is the function or the solution is associated with such growth. Remember, we said that over here, k is positive. Okay, so let's look at the situation for the exponential decay. Okay, so let's get a situation for the exponential decay. All right, so let's look at the diagram for the exponential decay. So let's have a diagram as this. let's call our horizontal as the same as time, and our response variable as y. And so the nature of the exponential decay will just be, as we since it's since it is decaying, it will just approach 0. So if I have to say there's a decay, it must approach 0. Okay, so we have something as this. I think I'm not giving it my best shot. Okay, so this becomes our P naught. This becomes our P naught. This point becomes our P naught. Okay, very good. So with this, over here we claim that k is less than 0. If k is less than 0, it just means that our P will just be equal to P naught e to the power minus kt. Okay, so in such instance, we say that's exponential decay. So in such distance, in such instance, we call it the exponential, decay. So please let's take note. All right. Before we dive into some examples, let's look at a theorem. Okay. So the theorem, so we have a theorem that we that would help us to solve several problems. Okay, in physics and in biology and in other disciplines as well. So let's take note of that. Okay. So suppose that the decay rate. So suppose the decay rate. Okay. Suppose the decay rate. Let's call it. Let's say K. Let's call that K, and then the half-life. The half-life. Let's denote that as big T are related. Suppose these are related. Suppose they are related by kt equal to then lane of 2. So out of this, I can ask you to kind of, determine the decay rate and then the half-life of any organic matter, right? So based on this theorem, we can leverage such theorem to kind of solve some real world situations, and with time you'll be able to know how all of these things play out well, or even help us to understand life. Okay, it's so important that mathematics is so important, and it underpins everything that we do, being it in finance, being it in economics, being it in physics, being it in biology. Okay, mathematics is so important. So I want us to take note of that. All right. So with this, what it means is that I can over here I can determine so many things. I can kind of find the decay rate. So it just means that our decay rate in this case will just be what, lane of 2 out of the half-life. Okay, and then also half-life. Okay, half-life will just be equal to t equal to the lane of 2 or divided by the decay rate. Okay, so if you already know your decay rate, it's easier to find the half-life. Okay, and I would like to sort of point out that this theorem, it's so important that even when we know the decay rate of an organic matter, we can determine its life, its half-life. Okay, and also if we know the half-life, we can also determine how long it has decayed. So I want us to sort of take note. It's also important. Would As I mentioned, we will use this theorem a lot, so I want us to take our time. The most important thing is to have this in mind. Okay, is to have this in mind. So please take note. All right. All right. All right. So let's look at the first problem of the day. And plutonium-239, a common product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about 0.0028% per year. Now the question is, what is its half-life? What is its half-life? So already we have already established a theorem, um, and so we are just going to use a theorem to solve such problems. Okay, so let's take note. But then we mentioned that the decay rate and then the half-life are related this way. So solution. So solution, we said that the decay rate and then the half-life are related this way. Okay, good. Now, if we are asked to find the half-life, which we denote it as T, it then means that our T would then be equal to the length of 2 or divided by K. Okay, but in this question, we are very fortunate because everything has been given to us. We have the decay rate to be 0.0028%. Okay, so we just have to kind of put in the value. And what would that value be? Has anyone solve this? So the final, so first, I know somebody has already given us the answer, but when you convert the percent into that, we should have something as this, and that should give us what? That should give us 24,755 years. Okay. So I want us to kind of take note. So now we know when to kind of find the half-life of any organic matter or anything that has to do with probably the decay and the half-life. Okay. So if I give you any, probably is somebody died, let's say 4 years ago, and we want to find the decay rate, well, as long as we know that it's life half-life, we can kind of use this relation to kind of make an approximate either half-life or a decay rate. Okay. So please, I want us to kind of appreciate all these applications. And then I want us to look at another interesting question. So that will be more or less like a follow-up question. So the B part is that the half-life of barium 140 is 13 days. Now the question is, what is its decay rate? So the decay rate, we denote it as K. So that should give us the length of 2 or divided by T, right? But then the half-life of the barium is given, which is what, 13, right? So we divide this by 13. And that should give us what? What would the answer be? So that should be 0.053 per day, right? So in percent, that'll be like 5.3% per day, right? Good. So the beryllium 140 will be decaying at this rate. Okay, so let's take note of that. So let's kind of another interesting question as well and see how best we can use the same principle to address it. Okay, all right. So the radioactive element carbon 14 has a half-life of 5,730 years. Now, the percentage of the carbon-14 present in the remains of plant and animals can be used to determine age. Archaeologists found that the linen wrapping from one of the Dead Sea scrolls had lost about 22.3% of it carbon-14. Now, how old was the linen wrapping? How old was that? So with this problem, what we will do is that we'll take our time bringing the problem into simpler form, then we see how best we can solve it. Okay. So let's take our time as we do it together. So already we know that the half-life is given as 5,730 years. Okay. So we know our K, so the half-life is represented as T. So already we know our T to be the 5,730 years. Okay. And then we also found out that the archaeologists found out that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon 14. So if this if there's a loss, which is 22.3% is a loss, then we have to find the remains of that, okay, the remaining part of the carbon 14, okay? So we have to find the remaining part. So we just have to subtract from the 100%, and that should give us the remaining of carbon 14. Is that okay? Good. So we'll take our time to kind of approach this. So from the first scenario, we can, we know the half-life, so it means we can find the decay rate, okay? So if so for this, since we know that, let me use a different pencil. All right. So we know the half-life to be what? 5730. Okay. That means that we can determine its decay rate. In that case, our K should be equal to what? What do you think our K should be? So by using a calculator, you should get something like 0.000120 and then 97. So that will be the the decay rate. Okay. Now, so in that case, if that's the case, then what it means is that now remember that when we were looking at the exponential growth rate, we said that problems in that nature can be solved using such problems can have their solution in this form. If you could recall, if you could recall, we had it this way, right? So I want us to kind of take note of this. So if that's the case, we can plug in this, okay? If that's the case, we can plug in. If already we know our decay rate, we can just plug in this. So we know our decay rate to be equal to 0.000012097T, okay? So it means that the general solution to this will just be this. This is just going to be the general solution, okay? As far as this problem is concerned. But then remember that the question went further to say that the archaeologists, let me underline this, says that the archaeologists found that the linen wrapping from one of the Dead Sea Scrolls had lost about 22.3% of its carbon 14. Okay, has lost that. So we have to find the remaining part of the carbon 14. If this is lost, that means we have to find the remaining part, right? So the remaining part, what I will do is that, so remaining part, so let me take my time to use probably a different. So I will say the remaining percentage of carbon-14. What do you think will be the remaining part of carbon-14? Can anyone help us? If we are given that 22.3% of carbon-14 has been lost, then the percent of the remaining carbon-14 will just be what? That'll be 77.77%. Okay, good. In that case, it means we're going to have our P of T to be equal to what? To be equal to what? Somebody should help us. Okay, that'll be 0.777 P naught, right? Good. Because the decay, because this part has been given to us, okay? This part has been given to us, which is 0.777, okay? But then the initial value of that was not given, so that's why we have that. So now, since we have these two, what we are going to do is that we're just going to equate them together, okay, so that we can determine the how old the lining. We can determine the age of the lining wrapping. Okay, good. So let's take notes. So by equating them together, if we should equate them together, in that case, we're going to have what? So by equating them together, we're going to have P naught e to the power minus 0.000120970 to be equal to what? 0.777 P naught. Okay? So you can see that the P naught can cancel easily. So you can just cancel them right away. So we are left with only this one to solve. Is that okay? So we are left with only this to solve. So we are left with only this to solve. Okay, now the question is, how do we find T? Now, for us to solve this, what we will do is that because of the exponent, because of this nature, okay, because of the problem of this nature, we have the exponent. What we can do, we can use we can take the natural log of both sides, okay? And the reason why we're using the natural log of because the natural log and then the e, okay, and the e, they are inverse of each other, so it is easy to use that, okay? So let's do a quick recap over here that the length of e is always 1, okay? Because the reason is because they are inverse of each other, so it can easily use that. The length of e is always 1. So we can take the natural log of both sides. So by taking the natural log on both sides, you're going to have something beautiful as this. So in that case, you're going to have negative 0.00120,970 equal to what? Then what would be the length of that? So let's just, maintain it this way, then use the calculator to give us the result. So in that case, my T will be equal to what? All right. So what will be the final result? Our final result should be what? Should be 208 what? If you use a calculator, you should get this. So what it may just means that the line and wrapping from the Dead Sea Scroll is about it's about 2086 years old. So So this is how we can kind of approach such a problem. So let me do a quick recap of what we studied. And so with this problem, we're fortunate that the half-life was given straight away. So if they already have your half-life, so it means it's easy to calculate your decay rate, and that's what we did over here. So we went straight away to calculate our decay rate over here. We had a decay rate of 0.0001297. And remember, because this problem has to do with decay, so it just means that there's exponential decay comes into play. So we invoke the theorem on the exponential decay, and we said that the general solution for any exponential decay can be given this way. Okay. All right. So since already we know our decay rate, which is k, which is 0.0001297, we kind of plug it back into the general solution, and that means we have this. Okay. Now, remember that in this problem, the archaeologists found that the linen wrapping from one of the Dead Sea straw had lost about 22.3% of its carbon 14. So what it means is that we can just straight away find the remaining percentage of carbon 14. Okay. And which means that the remaining will just be what? 77.7%, right? Good. Is that if that's the case, we can just plug it back. What it means is that this part has been given to you. It just means that the E to the decay factor has been already be taken into account. So you only have to multiply it by the initial population growth, or the initial um what's the name? The initial the excuse scroll. Okay. All right. So let's take note of that. And now, since we have these two, what we can do is that at this point we can just, equate them to just find the time, okay, or how old the age of the lining, the lining wrapping. So we can equate them, and by equating them over here, what we saw was that P naught was common, so we can just cancel them out, and then at this point, because of the exponential function over here, what we do is that we take the natural log both sides. Why did you take the natural log both sides? Because the natural log and the exponential functions are inverses of each other, okay? E, and then there's the E, and then the exponential functions are inverse of each other. And then we claim that the length of E is always 1, okay? So I want us to take note. And by solving it, we had this. So over here, we claim that the line and wrapping is about 2086 years. Okay, so let us take note of this, and this is a very interesting problem. All right, so let's get another interesting problem for this episode. Let's get another interesting problem. Now, in this problem, we were told that following the birth of their daughter, two grandparents want to make an initial investment of peanut that would grow to $10,000. Okay, by the child's 20th birthday, interest is compounded continuously at 4%. Now the question is, what will be the initial investment? Okay, or what was the initial investment that was made on behalf of the child. So let's look at this problem and see how best we can address it. And these are very practical, and these are things that goes on in finance, in the banking industry. So it's important that we know what goes on there. For instance, if you go to the bank, hey, you want to make an investment, at least these are some of the questions that you can be asking. That is it growing? Is the interest going to grow continuously, or is just going to be a simple interest? So all of these things, these are some of the questions you need to ask the bankers anything you want to make investment, because we are investing, so you want to make sure that the yield on your investment is good, right? Good. So let's see how best we can solve this problem. Over here, there are some key elements for us to take note. Remember that it is expected that the initial investment of P naught will grow to 10,000. Okay, so let me underline that 10,000. So this is what we expect to get at the end of the day, at the end of the investment. This is how much we want to get. All right. But remember that it was said that the interest is compounded continuously at 4%. It's compounded continuously. If it's compounded continuously, in other words, it should grow exponentially. Okay. If something is compounded exponentially, we expect that thing grows exponentially. So which means that we can use the theorem of exponential growth over here, okay? We can invoke that theorem at this section. So let's take note of that. All right. But remember that in this problem, the initial investment, which is P naught, was not given. So that's what we are asked to do. So please, let's take note. All right. So we said that the general solution of any exponential function or of any exponential growth or decay can be solved using this. Okay. The general solution of any exponential decay is this. Exponential decay or exponential, in this case, is growth because it's compounded. So that becomes a growth. Okay. So we are using this. All right. So let's take note. Now, what is our K in this question? Our K is already given because it said that interest is compounded continuously at 4%. So it means our K is our what? Is our 4%. So let's take note. Then what about our final value? Our final value was given. So at the final time, we're kind of given, right? So by the 20th birthday, so that becomes our final value. We want to have a value of 10,000. So okay. So if that's the case, it means that our at time 20 at time 20 we're given. Okay. So at time 20, let me kind of take my time and break it down so that everybody will get it. All right. So already we are given that. Let me take my time. So at time 20, we expect to have this money. Okay. At time 20, we expect to have this. And then our K in this problem was given us what, 4%, right? So we have everything we need to solve this problem. So what we need to do is to solve for the initial investment. Is that okay? So please let's take note even as we solve this. So we have this. So by plugging this into that, we should, if we plug this, into the general solution, we should have 10,000 equal to, we don't know our P naught, we maintain it. And then our K is 4%. 4% should be give us what? 0.04. And then our T was what? Our T from the question was 20, right? All right. So in that case, we should have 10,000 equal to, what is this side? That should give us what? P naught equal to point what? 0.8. Now, so it means what this implies that our P naught will just be equal to what? 10,000 divided by 0.8. And then when you use a calculator, you should have what? You should have 4,000. You should have 4,493.29. So it means that the grandparents, for them to get for them to, yield $10,000 by the time their daughter's birthday is on the 20th, or by the time their daughter's birthday is on is on the 20th, okay, they would have to invest about 4,493.29. Okay. All right. So I want us to take note that this is very important, especially if you want to invest into their children's education. For example, if you go to the bank and you want to make such investment, there's some questions you may want to ask in terms of the interest. How is it going to grow? Is it going to be like a simple interest, or um it's going to be like a compound interest? Okay, or it's going to um okay, so it's going to be like a compound interest or something. You want to kind of take note of that. Okay, so please let's take note. This is a very interesting problem. So okay, so I want us to look at all right, so at this point I want us to look at um Newton's law of cooling. So Newton's law of cooling is one of the most important laws in physics, and it states that the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings. Okay, and I would want to mention that such process can be modeled with an exponential function. So please take note out. I would pick up one or two examples, then we can see how best we can leverage uh, the, the 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 principles of Newton's law of cooling. Okay, so please let's take note. All right, so let's look at what the law is about. Okay, right. So let's move on. All right, so on that note, if I have something like this, if I have the differential equation, all right. So what this is just going to be the temperature T of a cooling object, um, which drops at the rate that is proportional to the difference. Okay, to the difference where over here, remember the T is a temperature. Okay, that is cooling. Okay. All right. And then we claimed over here the C is just is a temperature of the surrounding medium. Okay. So please let's take note of that. Now, the general solution to this particular a differential equation can now be given us as this. So we claim that general solution let me use a different pencil. So the general solution of this will just be giving us this. So please let's have this in mind. This is the famous Newton's law of cooling. Okay, so I want us to take note of that. We said that the temperature T of any cooling object drops at the rate that is proportional. Okay, that is proportional to the difference okay, and the difference do with the temperature. The difference in this case, we're looking at the temperature, which is T, and its and its surrounding medium. Okay, and the temperature of the surrounding medium. So I want us to kind of take note, and we claim that the general solution of this particular process is this T of T equal to A multiplying E to the power minus minus KT, all of that, adding to the surrounding medium. So I want us to kind of, take note of that. Good, good, good. So let's take note at this point. Let's see how best we can leverage such principle to solve real world problem. All right, let's take note. All right, so the first problem of this is that a body is found slumped over a desk over a desk in a study. A coroner arrives at noon, immediately takes the temperature of the body and finds it to be about 94% degrees. She waits 1 hour, takes the temperature again, and find it to be 93.4%. She also notes that the temperature of the room is about 70%, sorry, 70 degrees. Now, when was the murder committed? When was the murder committed? Did you ever imagine that such a problem can be solved using mathematics? Do you think that problems like this can be solved using mathematics? So this tells you how powerful and significant mathematics is in terms of solving, real world situations. Okay, stay with me as we kind of explore how best we kind of solve this problem. We over here, what we're going to do, you're just going to leverage the principles of the Newton's law of cooling, which we have already sort of noted. Okay, and we claim that. So let's start with a solution. So we claim that the general solution for Newton's law of cooling, and let me state that again, with the Newton's law of cooling, we said that we have a differential equation. Let me use a different pencil. So this is the differential equation for the Newton's law of cooling, and we said that a general solution can be solved using can be solved as this, okay? And that's what we said. Okay. So where we claim that K will be your what? Your decay rate, and your C is the what? Is the temperature of the surrounding medium. Okay. So please let's take note of that. Very, very, very important. So let's take note of that. Please, is that okay? Good. If you at this point you have any questions, please let me know. And if you have not subscribed, please hit on the subscription button, and then also turn on the notification button, so that anytime I release new content, you'll have access to that. All right. So let's go on. All right. So let's see how best we can solve this. But then we can pause the video for a second and try to see how best you can approach this problem. Now, so what we can do is that to solve this problem, what we can do is that we can let t to be the time elapsed, okay, in hours. Okay, and then where t equal to 0 represent the noon. Okay, so this is how we are going to approach this problem. All right, because the question says that a body is found slumped over a desk in a study. A coroner arrives at noon and immediately takes the temperature of the body and finds it to be so. So it means that the whole thing started at noon. So at noon, it means this is the initial time that the whole thing took place. Okay, is that okay? So we letting the time to be 0 would represent our initial time. Time always start from 0. Okay, time always start from 0. So we assume that time at time 0, which is the noon, is where the coroner first, came in to take the first reading. Okay. Okay, is that okay? All right. So I want us to, take our time to explore this particular problem. Okay. So the coroner arrives at noon, immediately takes the temperature of the body and finds it to be 94.6 degrees. Okay. So what does this represent? The 94.6. What does it represent? The temperature of the body is giving us this. What does it represent? That becomes our T of T. So at time zero, you're going to have, so at time zero, you're going to have e to the power. And remember, our T is zero. So you're going to have this at time zero. But at time zero, the temperature of the body was what? Was 94.6. So what it means is that whenever I see T of zero, I just replace it by what? 94.6. Okay? Is that okay? Remember, e to the power zero will be 1. Okay, so in that case, you're going to have, and what to be our C? Our C was giving us what? Now, when you go further to read, it says that she waits 1 hour, takes the temperature again. There was a temperature I was taken again, and finds it to be 93.4%. It's 93.4 degrees. Sorry. She also notes that the temperature of the room is 70 degrees. So the temperature of the room becomes our C. That was what I explained earlier on. So that's our C, which is what? 70. Is that okay? So in which case my A should be equal to what? Which would be 24 point what? Point 6. All right. So if that's the case, it means we can just plug this back into the main general solution, right? So if that's the case, it means our T of big T of T equal to A multiplying minus KT plus, already we know our A, so we just have to, let's plug it back. We know our A here. So our A is what? 24.6. But our C, we also know our C to be what? To be 70. Is that okay? So now we have our general solution as this. We have our particular solution as this, because now, so we can say is the general solution because we have not also found our K. So we can still have it this way. All right. Now the question is, how do we go further to find K? So for us to do so, there are other things that I would want us to explore. Okay. For us to do that, there are other things that I want us to explore further. Now, to find the number of hours, since the murder was committed, we must first find K. That's as mentioned. That's our decay rate. Now, we should use the fact that at T equal to 1, the body's temperature was 93.4 degrees. Remember, that was what the question said. Because the question says that she waits 1 hour, takes the temperature again. She waits 1 hour. So we are using that fact that at T equal to 1, the body's temperature was 93.4 degrees. That was what the question, pointed out. Okay, so please let's take note. So at T equal to 1, all of these things we are just, burden on what the question said. Okay, so at T equal to 1, the body temperature was 93.4 degrees. Now, having these two, information, we can just still plug it into the into the general solution. Then we can now solve for K. Is that okay? Good. Now, at T equal to, so at T equal to 1, we're going to have T of 1 equal to 24.68 to the power minus k multiplying 1 plus 70. Okay. Now, what is T of 1? Remember, T of the temperature was discovered to be what? 93.4. Then we solve for K. Okay. Now, how do we do that? We just do one or two arithmetic, and we should get something like 23.4 equal to 24.6 multiplying 8 to the power minus k. Now, at this point, since we have the exponential function in it, I'm going to solve for k, which is at the exponent, we can use what? We can use a, we can take it the natural log both sides. But before that, let's divide both sides by 24.6 so that to be easy for us to solve, right? Good. So please, let's take note of that. So in that case, we're going to have e to the power minus k to be equal to 23.4 all divided by 23.6. So at this point, what you do, we can take the natural log of both sides, the natural log of both sides. So by taking the natural log of both sides, you're going to have something as this. Okay. And remember, we said that the natural log and e are inverses of each other. So I said that the natural log of e is always 1, okay, which means they're inverses of each other. So in that case, we're going to have minus k equal to the natural log of that. And what is this? This should give us what? This should give us what? Minus 0.05. So this implies that my k will just be equal to what? 0.05. Okay. 0.05. So I want us to take note. So in which case we're going to have our particular solution to be equal to what? To be 24.6 e to the power minus 0.05t plus, already we know our c, which was 70, given the question as that. Very, very important. Already we know that. Now, remember the question was that, remember the question we were given was that, when was the murder committed? When was the murder committed? So so at this point, this is where we have to also take our time to do one or two analysis before we jump into this. Okay, so let's see how you can pause the video and see and think about it. What do you think will be the time that the murder was committed? What do you think that time will be? So let's think of it for a second, see what we would get. So over here, we can come up with our own we can come up with our own assumption at the time of death. I mean, come up with our own assumption as far as the temperature of the body was concerned. Because when you look at the problem, so for example, if I'm a CID and I want to solve this problem, there are certain things I can do in order to know when the murder was committed. Now, remember that at the time a coroner arrives to take the temperature of the body, it was found out to be 94.6 degrees. That was the time that was the time. Remember the murder, the body was found slammed over over a desk, right? Good. That was the time that the murder had occurred. Now, at the time that coroner had arrived to take the temperature of the body, it was found out to be 94.6 6 degrees. So which means that the person could have a normal temperature of about, let's say, 98 point something degrees before the method occurred. Before the method occurred. Is that okay? Does that make sense? Because the temperature of your body before you become unconscious will be different, right? Will be different. So in our case over here, Corona found out at the time of death was like 40, so it means was about 94.6, which means the number temperature could have been like 97 point something or 98 point something degrees. Okay. So in our case, let's make an assumption that the normal temperature of the body was around, let's say, 98.6% degrees. Okay. So we assume over here, we're going to assume that. So we're going to assume that the normal temperature of the body, okay, was let's say 98 point, let's say, 6 degrees at a time of death. Okay, so let's take note of that. So we are just going to use this. So if that's the case, now having our particular solution as this, we just have to plug it inside, and that will give us what? That should give us 98.6 degrees, equal to, already we kind of know everything that we have, plus 70, right? Because we have everything that we need. All right, so at this point, we just have to do our arithmetic, and that should give us what? E to the power minus 0.05t. Let me take my time over here. Equal to what? That should be 28 point what? 6, or divided by 24.6. Over here, the same thing, we apply the natural log on both sides. So by applying the natural log on both sides, we should have e to the power. You should have minus what? 0.05t equal to the natural log of 28.6, or divided by 24.6. And that should give us what? T to be equal to what? If you use a calculator, that should give us minus 3.01. But what does this mean? Remember the question, our question was that, when was the medal committed? When was the medal committed? So how do we interpret this? How do we interpret this result? How do we interpret it? So since t equal to 0 represent noon, remember the noon was a time that the meta occurred. Okay, let's kind of go through the problem again so that we can appreciate it well. So remember that the body is found slumped over a desk in a study. The coroner arrives at noon, immediately takes, so we can assume that noon, noon was a time that coroner arrived to take, the reading. Okay. Okay. So if that's the case, now if you want to know when was the method occurred, it just means that the method occurred before noon. Is that okay? It just means that the method occurred before noon. Now, if that's the case, how do we interpret this result, which is t equal to minus 3.01. So since t equal to 0 represent noon, it just means that the time of death was about 3 hours earlier. Is that okay? If t equals 0 represent our noon, it just means this result, remember it is minus. So if you have t equal to, remember your t is time. If time is negative, it just means that you have to move backward. You have to read backwards, right? So it just means that the time of death um was about 3 hours earlier, or at about, let's say, 9 o'clock a.m. Okay, so this was the time that the murder was committed. I believe you've been able to kind of learn a lot tonight. You've learned a lot in this episode, and I believe that from now onwards, you begin to appreciate mathematics and the role that mathematics is playing in our community. Okay, so please, at this point, you have not subscribed, please do so. And also share this good news, this nice and quality content with your colleagues and loved ones. And I believe that this will also be a blessing unto them. I would like to kind of emphasize that my content is to kind of take away or to diminish, demystify the myth that surround mathematics. A lot of people have a lot of mindset about that mathematics is only for the geniuses. Mathematics is not creative. Listen, math can be broken down into the simplest form for you to understand it. So please and please again, join me and I'll make sure that your time with me will not go wasted. I'll make sure that I'll give you the best. I'll break it down to the simplest possible for you to get it. So stay with me. All right. So let's take a pause and we'll come back. All right. Take care.